There's a moment inside every electrolyzer stack that no investor ever sees, no financial model ever captures, and almost no project developer truly prices in. It doesn't happen at the scale of megawatts or pipelines or hydrogen storage caverns. It happens at the scale of millimeters. A barely visible imperfection about 3 millimeters across inside a polymer membrane. And yet that tiny defect can quietly drain millions of dollars from a green hydrogen project long before anyone realizes what's going wrong. To understand why, you have to go beneath the plant, beneath the balance of plant, beneath the control systems, and into the electrochemistry itself. Because at the heart of every PEM electrolyzer is a membrane that does something extraordinary. It allows protons to pass through while blocking electrons and gases. It separates hydrogen from oxygen. It maintains the integrity of the entire reaction. In many ways, it is the system. But the membrane is also fragile, not in a mechanical sense. Modern membranes are engineered for durability, but in a system sense. Because the membrane doesn't operate in isolation, it exists at the intersection of chemistry, temperature, pressure, water quality, and electrical current density. And any imbalance in those conditions begins to stress the membrane in ways that are not immediately visible. Now imagine a defect, not a catastrophic tear, not a full failure, just a small irregularity, 3 millimeters. Maybe it's a manufacturing inconsistency. Maybe it's a localized impurity. Maybe it's the result of uneven hydration during operation. It's small enough to pass quality checks, small enough to be ignored, but it changes everything, because that defect becomes a point of resistance inside the system. In an electrolyzer, current density is supposed to be distributed evenly across the membrane. That's how you maintain efficiency. That's how you avoid hotspots. But a defect disrupts that balance. It creates a localized area where resistance is higher or lower than expected. And when that happens, the current redistributes itself. Now you have uneven current density. Some regions of the membrane begin to work harder than others. They generate more heat. They experience higher electrochemical stress. And over time, those regions begin to degrade faster. Not across the entire stack, just in specific zones, which makes the problem incredibly difficult to detect. Because from the outside, the system still looks like it's working. Hydrogen is still being produced, the plant is still operating. But efficiency begins to slip. Not dramatically, just slightly. Maybe 1%, maybe 2%. But remember, hydrogen economics operate on razor-thin margins. A small drop in efficiency means more electricity per kilogram of hydrogen, and electricity is the dominant cost. So that tiny membrane defect has now become an energy cost problem. But it doesn't stop there, because uneven current density also affects gas crossover. In a perfectly functioning membrane, hydrogen and oxygen remain separated. But when the membrane is stressed, microscopic pathways can begin to form. Not large enough to trigger alarms, but enough to allow small amounts of gas to cross over. Now you have hydrogen mixing with oxygen. At low levels, this doesn't cause immediate failure, but it introduces safety risks and reduces product purity, which means additional downstream processing, more compression, more purification, more cost. And now the system begins to layer inefficiencies on top of inefficiencies. Meanwhile, the localized hotspot created by the defect continues to grow. Heat accelerates chemical degradation. The membrane begins to thin in that region. Catalyst layers start to lose activity. And what was once a 3 millimeter imperfection begins to expand. This is how failure propagates in electrolyzers. Not as a sudden event, but as a slow compounding process. And here's where the economics start to unravel. Because electrolyzer stacks are not replaced one cell at a time. When performance drops below a certain threshold, you replace the stack. That's a capital event, planned years in advance, modeled carefully in financial projections. But when degradation accelerates due to localized defects, that replacement comes earlier than expected. Now your capital expenditure increases, your depreciation schedule shifts, your internal rate of return drops, and your entire financial model begins to drift away from reality. But the real problem is not the cost of replacement, it's the uncertainty. Because once a defect like this exists, it's not isolated. It raises questions about manufacturing quality, operational conditions, and system design. Investors don't just see a technical issue, they see risk. And risk translates into higher cost of capital. Now that 3 millimeter defect is affecting financing. Lenders begin to ask for higher contingencies. Insurance premiums increase. Performance guarantees become stricter. And suddenly, the project that looked bankable on paper starts to struggle to reach final investment decision. This is how micro-scale issues become macro-scale barriers. And it's happening more often than most people realize. Because as the industry scales, manufacturing volumes increase. Quality control becomes more complex. Supply chains stretch, and the probability of small defects entering the system rises. At the same time, projects are being pushed to operate under more dynamic conditions. Variable renewable energy means frequent load changes, start-stop cycles, thermal fluctuations, all of which place additional stress on the membrane. So you have a system that is both more vulnerable and more stressed. And this is where the real engineering challenge lies. Not in making membranes that work in perfect conditions, but in designing systems that can tolerate imperfections. Systems that can absorb variability without cascading into failure. Some approaches are already emerging. Advanced diagnostics that monitor localized performance within the stack. Not just overall efficiency, but spatial variations in current density and temperature. Early detection systems that can identify defects before they propagate. Improved materials that are more resistant to chemical degradation and mechanical stress. Membranes with enhanced durability under dynamic operating conditions. Better water management systems that maintain consistent hydration across the membrane. Because uneven hydration is one of the key drivers of localized stress. And perhaps most importantly, system-level design changes that reduce the impact of variability. Hybrid energy inputs, buffer systems, operational strategies that prioritize stability over peak output. These are not incremental improvements, they are shifts in how hydrogen systems are designed. Because the industry is starting to realize something critical. Efficiency alone is not enough. You can have the most efficient electrolyzer in the world, but if it cannot maintain that efficiency under real-world conditions, it will fail economically. What matters is stability, consistency, the ability to operate within a narrow performance band despite fluctuations, imperfections, and stress. And that brings us back to the 3mm defect. Because it's not just a defect, it's a signal. A signal that the system is operating too close to its limits, that there is not enough tolerance built into the design, that small deviations can cascade into large consequences. And this is the core challenge facing green hydrogen today. Not whether we can produce hydrogen efficiently, but whether we can produce it reliably, predictably, and at scale without being derailed by the smallest imperfections. Because in a system this complex, perfection is not realistic, but resilience is. And the projects that succeed will be the ones that are designed with that reality in mind. Not just optimized for best-case scenarios, but engineered for worst-case conditions. Because in the end, hydrogen doesn't fail because of big problems. It fails because of small ones that no one thought would matter. Until they did. And this is exactly the layer we break down inside H2 Hub by Renee Energy, where engineering meets economics and where real-world hydrogen systems are tested not for performance, but for survival. Because if your system can't survive a 3mm defect, it won't survive the real world.